Hello everyone, welcome to this video where we will discuss the matching in graph theory. Getting started, we have the outline here. First we will cover the introduction, means what matching is. Then we will go to see the terminologies related to matching. Then we will see what is perfect matching and number of perfect matching in complete graphs. And also at last we will discuss the difference between maximal and maximum matching. So in introduction, we can see this illustration where there are some possibilities of caps, some possibilities of t-shirts, and some possibilities of shorts. So for any person to wear any combination of these, he will have to match any of the cap and connect it with any of the available t-shirts, forgetting the rest, and also connect it with any of the available shorts. So what we are doing in brief is we are selecting a vertex of one vertex set and connecting it to the another vertex of another vertex set by eliminating all the remaining. So here we will discuss what matching is, how it is related to degree, and some example with such real life application. So the definition of matching suggests that a matching in the graph G is a set of non-loop edges with no shared endpoints. Means no two edges will have a common vertex. In other words, matching in a graph is a subgraph where degree is at most 1 for all the vertices. Means the degree can be 0 or 1, not more than that. So here we have the graph G and there are 6 possible matchings of graph G. Here the red vertices represent the vertex which are not connected to any of the edges in the matching. So the green vertices similarly represent the vertex which are connected with edges. Moving forward, we have some applications of matching. Means we have some students in a university and so they will be paired up with respect to their compatibility with each other. This is a problem of matching. And also the matching of job with employee based on the employee personality and interests is also an example. Stable marriage problem is a huge problem that is based on matching, which can be discussed in another video. So here we have the terminologies for matching, what a saturated or meshed vertex is. So here we have written that the vertices incident to the edges of a matching are said to be saturated or meshed. Means in a matching, if the vertex has degree 1, means it is connected to any of the edges, then it will be said a meshed vertex or a saturated vertex. And the vertex which is not saturated, means have degree 0, will be termed as unmeshed or unsaturated vertex. So here in the example, we have the matching where 2 vertex are unsaturated and 2 are saturated. So M-saturated matching is a matching where M vertex are saturated. And M unsaturated matching in a similar way is a matching where M vertex are unsaturated. So our selected example is 2 saturated or 2 unsaturated. And the size of matching is nothing but the number of edges that are present in the matching. Moving forward, we have the perfect matching. So the perfect matching is a matching in which all the vertex of the graph are saturated. More technically, the perfect matching, the degree of each vertex is equal to 1. Means no vertex exists with degree 0. In the graph, the examples of matching are M1 and M2 considered here. In M1, there are 2 unsaturated vertex, so it cannot be a perfect matching. Whereas in M2, all the vertex have degree 1 and are saturated, so they can be termed as the vertex of the perfect matching M2. So here we have drawn another example with the black edge and one red edge, which are crossed each other. So in this example, all the vertex will be saturated according to us, but can it be a perfect matching of a graph G? No. Why? Because the graph G does not contain that red edge. So we cannot add an edge that does not belong to the edge set of the graph in order to form a perfect matching. Moving forward, we have two propositions. Uh, this simply suggests that number of vertices in a perfect matching is always even. Means if we are finding a perfect matching of a graph, then this graph should contain even number of edges. And consequently, the size of the perfect matching is n by 2, means the perfect matching should contain n by 2 edges, where n represents the number of vertices. Here we have illustrated that each vertex in a perfect matching is matched according to our definition. So degree should be equal to 1 for each of them. And consequently, the degree sum of the graph will be equal to n, where n represents the number of vertex. Before, we have the handshaking theorem, where we say that the degree sum is equal to twice the number of edges. Means the degree sum is always even. Here the degree sum is n, so n is twice of the number of edges. Means n is always n equal to h. The number of edges e is always a positive integer. Consequently, the number of edges will be equal to n by 2. Means the size of the perfect matching is always equal to n by 2, where n represents the number of edges in that graph. Sorry, number of vertices in that graph. Next, for this statement that number of vertices in a perfect matching is always even, the converse is not always true. Means we cannot ensure that if the graph has even number of vertices, it should have a perfect matching. Here are some counter examples. We can look after it. The first graph contains 10 vertices and the second one contains 6 vertices, but none of them have a perfect matching. Next, perfect matching in complete bipartite graph with equal cardinality of each partite set. Remember, we cannot have a perfect matching in Kmn where m is not equal to n. Means in a bipartite graph where the partite sets are of different size, we cannot have a perfect matching. Why? Because in a bipartite graph, the edges exist only between the vertices of different partites. Means we cannot connect a vertex x1 belong to x with another vertex x2 belong to that same partite set x. So if number of vertex in x and number of vertex in y are not same, then we cannot form a perfect matching. Why? Because the greater cardinality set or the greater size partite set will have some vertex left unsaturated. So now our topic is complete bipartite graph with equal number of vertex in each partite set. So the possible number of matchings is n factorial. How so? Let us discuss. X1 can be connected to any one of the available vertex of y. Means there are n possible pairs between x1 and any y. If we connect x1 with any of the y, there will be a less opportunity for x2 to be connected with. Means x2 will have n minus 1 possible y's to be connected. Consequently, x3 will have n minus 2 possible pairs, and so on up to xn, which will have only one possibility left. So by fundamental principle of counting, we will have to multiply the number of possible ways for each instance as we are considering all of them simultaneously. So the number of possible ways, which is also equal to the number of perfect matchings in a complete bipartite graph Kmn, is equal to n into n minus 1 into n minus 2 and so on up to n, which is nothing other than the n factorial. So now let us discuss the number of perfect matching in a complete graph. So we have considered only the even complete graphs, means the graph should have even number of edges in order that there exists a perfect matching. So in our graph, there are two number of vertices, v1 to v2n. So v1 can be connected with either vertex other than v1 itself. So v1 has 2n minus 1 possible pairs. Similarly, v1 is connected to suppose v3, then v2 will have either v4 or v5 up to v2n, means 2n minus 3 possible pairs. as B1 is paired with B3 and B2 cannot be paired with itself. So consequently, B3 will have 2n minus 5 possible pairs, and so on. B2n will have only one pair left. So by fundamental principle of counting, we have to consider all of them simultaneously. So the number of total ways that a perfect matching can be formed in a complete graph with vertex 2n will be equal to 2n factorial all divided by 2 to the power n into n factorial. So here is an example of K4. So in K4 there are 4 vertices, means 2n is equal to 4, so n is equal to 2. The number of total perfect matchings is equal to 3. So here are the 3 perfect matchings that can be found on K4. Moving forward, we have the comparison between maximal matching and maximum matching. So the maximal matching is a matching that cannot be enlarged by adding an edge. Means to a maximal matching, we cannot add one edge, else it will violate the property of a matching, that the degree of any of the vertices will exceed the limit, that is 1. So in contrast to maximal matching, the maximum matching is the matching with maximum size. Means out of all possible matchings in a graph, means a graph can have the matching with size 0 if we will leave all the vertex unsaturated and so on. So the maximum matching is the matching with maximum number of matching. So the maximum matching has size always less than or equal to number of vertices divided by 2. Means as we have discussed, the graph should have even number of vertices in order to have a perfect match, and the perfect match also contains number of edges equal to half the number of vertices. So the maximum size of a matching will be the size of a perfect matching, that is n by 2. That's why the size is limited with less than or equal to n by 2. So here we have considered graph L4, means line graph with 4 vertices is our example. On the left, there are 2 maximal matching, means we cannot add any edge to the graph. If we add any edge, then the vertex in between will have degree 2, which violates the property of the matching. But clearly, these are not the maximum matching. Why? Because the one at the right side is the maximum matching, means the number of edges is 2, which can also be a maximal matching, and also we cannot add any edge to it. Here are 2 important observations: that a maximum matching is always a maximal matching, means we cannot add any further edge to it, but the converse is not always true. So on the left, there are the counter example for the converse. Next, a maximum or maximal matching need not be a perfect matching. Means, as we can see, if we take the graph which we discussed in the counter example of the converse of first proposition, means the graph where there will be at least one vertex remain unsaturated in any kind of matching. So in that won't be a perfect matching, but that will have the maximum number of matching, then it will be called a maximum matching. And if we cannot add any further edge to it, then it will be called a maximal matching. So a maximum or maximal matching need not be a perfect matching always. Next, summarizing what we have studied here. So what we learned: the basic definition with an illustration and some applications in matching. Then the saturated, unsaturated vertices and the size of a matching. Then we discussed what a perfect matching is and number of possible perfect matching in complete graph. And at last, we differentiated between maximal matching and maximum matching. If you want to look forward it, the reference is also given. Means the introduction to graph theory book is what we have used as reference for the slides. It is authored by Douglas Stewart. And if you want the page numbers, so page number 107 to 108, you can use. Thank you for joining us in today's video.